later. Yeah, sure. No worries, no worries. Yeah. Should we start?
Can we move on to the research presentation?
Should we start now?
Yes.
Okay.
Yes, please.
Yeah. Okay. Yeah. Sure. So let me set out a bit. Yeah. Okay. So my research interest should be what I'm thinking about is like I think most interesting maps should be inspired by physics or rather things happening in the natural world. Okay. So what kind of maps I did? So my area is in the higher representation theory. So what does this include? Oh, okay. In this talk, I think I will throw some jargons such that I'm not sure whether you guys are connected to it or not, but I just throw some jargons if you are connected to it, and I will give definition or explain some technical lemma if I need it in my in my presentation. Okay. So mostly with categorification. So we are morally is like associate a vector space to a number. Yeah. Or a vector space is like you can think of algebraic topology is like associate groups to the Euler characteristics of some manifold. And what I do are connected to like low dimension topology, symplectic geometry. I don't really work in symplectic geometry, but I my theory is connected to this part of story and low dimension topology, and mostly I deal with is the category of representation of algebra. Okay, and these three are deeply connected is mostly due to the homological mirror symmetry. And they also connected to I mean my work are connected to sheaves of Hilbert scheme, although I'm still not an expert yet. So categorization grows from when Grothendieck make category theory. If it is because they want to deal with sheaves. Okay, they want to have some more structure on the cohomology theory. Yeah. And one more thing is like the break group action. So I look at the break group action in the logistic sense. So given a quantum group, I can produce a break group action. So I got a quantum group, and then I can produce break group action. And this part here will somehow give some not invariant. Okay. And then why there's a physics behind? Okay, there's a bar here is like I getting unknown here. I mean I think my grasp of knowledge. So they are related to the quantum theory of physics. In particular is the string theory. So string theory is used to unify forces. They are trying to unify the gravity to the quantum mechanics. So I'm not sure if someone knows this. I just mention it out because I'm interested with this thing. So like the non-perturbative Chen-Simon theory. So they deal with the closed loop, closed string. Yeah. And then of course homological mirror symmetry suggested by Conservage in 1994 is because of this physics mirror symmetry. Okay, yeah, this is my interest. I just throw some word out even though I'm not very good with it, but I want to like let people see who are doing this field I'm interested to talk with. Yeah. So about my research, me and my collaborator Edmund Hang, we wrote a paper on this curves in this and a type B break group, and using the type B zigzag algebra, this is what we constructed, new construction. It's already submitted to the quantum topology, but it's still under referee. Okay, so how this project come from? Actually, this project rooted from this paper by Kovanov and Seidel. Seidel. Quiver. So this paper have three parts. It's a flow cohomology, symplectic geometry, and then quivers, algebra, and then this is a category, break group action. So we only do for topology and algebra. Okay, let's see what they did. So the subjects of the story is this play very important role in my research. So first of all, we have a thing called zigzag algebra. So it's an algebra in particular. So this algebra, you can think of it, I won't introduce the whole definition, but this algebra, you can think of it as a path algebra, but a certain quotient of a path algebra. So we take some more relation out of the path algebra. So in path algebra, the multiplication is just path concatenation. So you just concatenate path, and we only consider a quotient of it. And then we consider the projective modules over this algebra. Okay, and then this thing is generated by the idempotent in the algebras. So idempotence is something E squared equals, equal to E. It's like the projectors. It's actually the projectors. Okay, next sorry, next level, I want to look at the chain complexes of projective modules. And so the chain groups are the projective modules, number 2. And then chain differential, chain differential are the paths in the algebra. Okay, in particular, the quotient here will help to show that it is a differential. Next, we want to look at the category of number 3. Okay, so comp an. So in the category I need to tell you what's the objects and morphisms. So objects are 3, number 3, and then morphisms are chain map. Yeah. Okay. The final thing we will look at is homotopy category. So somehow we want to take some more quotient out of it. Of 4. Can I say 4? Just say maybe 3. There's an adjective of this. Okay, so what's the objects? So objects are chain, I should say number 3, up to chain homotopy. And then the morphism is again chain maps. Okay, maybe you wonder why we want to pass to chain homotopy category. So there's one technical lemma called Gaussian elimination. So if you, in your chain, you got an isomorphism, you can actually delete them. Okay, you can actually delete them. So we just look at the smaller stuff. So this is the category I'm working on. Once you have an isomorphism in your chain complexes, you can just delete them by this lemma. So I'm looking at the homotopy category. Okay, so yeah, okay. Okay, so what they did with this homotopy category. So there's an association between the objects in the category with the isotopy classes of curves in n punctured disk. Okay, so these are all curve up to isotopy. Curves up to isotopy, and then they should be like this. So something like this. Yeah, so if it is isotopy, then maybe I call it a P1, and then P2. P2 is the same as P. Okay. Yeah, just up to isotopy. And then what's interesting with it is there are group action on these two spaces. Okay, first of all, we talk about the topology part. So in the topology part, this is a classical theory that we can look at the mapping class group of the punctured disk. So the definition of mapping class group is a group of oriented diffeomorphism fixing the boundary and punches, okay, and then up to isotopy. So it's a result that the mapping class group of punctured disk is actually the type A break group. So one way to think about type A break group is, let me call it a name, is just removing the S square equals to identity relation in Sn. Okay, so they no longer square to identity. So that makes it infinite groups. Okay, so what Covanos ideal did is they built a group of bimodules functors. So bimodule is a module on left and right, possibly different ringed over different rings, so satisfying the relation of. Okay, so what this map do is they are intertwining operator. That means you can do it and then send over and then do it again. Is the same as, yeah, it's an intertwining operator. I don't want to explain more. And then what another result they show is this action is actually faithful. So it actually represents this thing here. So there's a faithful action into this. Okay. Yep. And then, okay, what we did is we produced another homotopy category using the new zigzag algebra. We call it a BM. And then we also have a topology story on the punctured annulus. So there's one punctured that's always fixed. So we call it an annulus. Maybe I get an n-1 numbers wrong, but just morally is a punctured annulus. Okay, dB. Okay. So we also have this association. And we also have a finite. Oh, okay, so sorry. I should say that there's a type B. So the mapping class group here is the type B break group. So type A and type B break group has the differences is in the relations of the group. Okay, and then similarly we also have a faithful intertwining operators. Yeah, faithful break group action. Moreover, we connect the two pictures together. So on the category side, it's like the tensoring over complex number. On the topology side, it's like taking a Z mod 2Z map. Yeah. Okay. So next bit. So how about what I'm going to do in future or currently doing, at least. So my supervisor gave me this project here. So how about look at the direct product of the zigzag algebra. Okay.
Actually, before you move from this,
yeah.
For the previous paper, right? Could you describe what was your contribution to this project? What was Heng's contribution?
what's hand combination, what's
Yours, yeah, for this
okay, okay.
project.
So okay, yeah. So actually, this project, this idea given my not okay. Actually, is my professor's friends suggested how how we how we make this zigzag algebra.
Mhm.
So my friends sorry. So my friend's contribution. There's not too clear I mean clear distinction what we did what mostly we both involved together, but I would say that
Mhm.
his would be mostly on the algebra part, like checking the satisfying relation, whether the bimodule functor checking satisfy the relations of the break group, and also maybe like tensoring over when this algebra tensoring over Z is actually an. So that's why his work is on generalizing this, looking at different maybe dihedral group producing this, and then I will I will I so I gave I look at this part here, and then I try to associate curves to how to say how to the chain complexes, associate chain complexes, but almost yeah we almost did the same thing, but like cross checking each other, and then yeah
Okay, thank you.
maybe it will make clearer like what maybe what is my maybe my advantage in the what I'm going to do later. I
Okay.
mean going to do now, yeah. So my sorry so my supervisor asked me to look at this direct product of the zigzag algebra, type A zigzag algebra. So vector space wise is just an times m times, and then you have some sm action of it. It's a direct product, so there's some non-triviality on defining the group action, but that's okay. It's not important for now. In particular, we look at this particular particular case here. So a 2n minus 1 cross n direct sum with xn. So what I did in my last part of my thesis is uh, so given a set of n crossingless matching, on the tree sphere. So crossingless matching is the multiple non-intersecting curves with endpoints up to ambient isotopy, and I associate them to a chain group in the a2n cross n projective module. Okay, and what I use here is, so I'm just telling what I use because so that people's know what I learned. Maybe I use the combinatorics in SN. So in particular is those the Koska-Fox polynomial. Yeah, Fox polynomial. And then actually I haven't quite give the chain differential yet. So the next step will be to extend it to a chain complex. Maybe you will ask why would I do this? I will explain in the next slide. So yeah. So first to do this, I need to understand the homomorphism space in this category. So it's expected to be presented using tools. Need to create the graphical calculus and then work out the basis. So why is this interesting? It's actually because if you take some crossingless matching And then you do some break group action. Okay. And then maybe something like this. If you close it one way, let me call this a Q, this is a P, and this is the break. Actually, you will get a link. Okay. So under the correspondence I gave you just now, sorry, this will correspond to tensoring chain complexes. And if you look at the Grothendieck group, or another word, the Euler characteristic of these chain complexes, we actually hope to get the Jones polynomial. And Jones polynomial is an invariance of Lie. And this guy live in a two category actually. So there's a objects morphism and two morphisms. So this, if this is done, it will be called a two categorification of of Jones polynomial. Yeah. And then three that I want to mention is I would like to learn more about like the algebraic geometry part. So it's like the connection of this algebra to other homotopy, or more precisely should be a derived category of some geometry objects, maybe sheaves on Hilbert schemes. Or Lagrangian, in symplectic sense, Lagrangian on Hilbert schemes. Yeah, this number 3 is what I would like to pursue, and 2 and 1 should be what I should calculate. Yeah. But because this is 20 minutes, so I just gave whatever I can give. And I also written out a research statement in my website. Sorry, I can't hear Peter. Is Peter talking?
Okay, yeah. Thank you. Thank you very much. Are there any questions?
Did you have 2 papers in your CV?
Oh, yeah. I mean, is it I removed one already because we combined the 2.
Oh, you combined the 2 papers.
Yeah, we combined.
Okay, so
I already resent my CV to Miss Chen. We combined the 2 papers. About 70.
So there were 2 in the past, but you combined them. Okay,
yeah.
That's good.
Yeah.
Right.
Sorry. Yeah.
But I think I asked my question already earlier.
Yeah.
Okay, so I guess the question I want to ask maybe other than people in your group, in your immediate group, which means your professor and Edmund, and the other postdocs and students he has, do you have contacts outside your group that you might possibly work with?
Unfortunately, don't have. Unfortunately don't. Just Edmund.
Yeah. Okay. Are there any other groups other than your advisors group that does research in this area?
Yes. Because I joined their seminar. Their seminar are in US, but I didn't make like connection to them because like the time zone is different, and then we haven't really have a chance to talk to each other yet. And then
can you name some other universities, departments where people do similar to yours?
Yeah. So it's like this guy here. So the Kovanov in the Columbia University, and then UC Davis. I think there's one guy. I forget the name now. UC Davis. There's a pretty big group in US. Mostly lead by this Kovanov. The journal we submitted is also he's the chief editor. He's my supervisor senior.
Okay.
Yeah.
Are there any people working in Asia?
Asia.
I'm in this.
I know, not really close, but also on representation theory. I know about one guy doing postdoc in. I don't know him, but I heard about him. He's actually Malaysian, also I think. It's called Christopher, but we never met him. He's used to be my supervisor's master student, and then he now is postdoc. Yeah, not directly the same, but closely related.
Okay.
Yeah. I mean Asia. I checked NUS. I think NUS got quite a few representation theories.
Yeah, that's true. Yeah, they do have some representation theories. Okay. So I guess one downside is that you did your end of your PhD in the COVID pandemic, right?
Yeah, correct.
So you never had a chance to travel to conferences to give talks.
Yeah.
Yeah, that's unfortunate, right? Because it'd be nice to be able to meet these people. But hopefully you can at least make connections in Singapore or something. Yeah. Okay. Yeah, because you're quite unlucky. Because normally at the end of PhD is when at least my advisor send me out to conferences and things like that to give talks to meet people. You never had that. Okay. So I guess one thing that maybe is good that if you do end up working here is that you really have to work hard to make those contacts. Yeah. Because you didn't have that in your end of your PhD because of the COVID. Okay. I guess the question is that how confident are you that you're able to, let's say you come here, right?
Mm-hmm.
How confident are you that you're able to keep writing papers away from your advisor?
I think, how confident am I? I'm not confident, but I think there's only the way I have to survive if I still want to stay in academic. So if I accept this job, then I will try my best to. Because even now, because I also meet less with my supervisor, because this project given to me is his work 10 years ago. So he also can't really give much feedback to me. So mostly I also learning myself, and then that's why.
That's good.
Yeah.
So you've been independent for this project.
Yeah, he's actually working on the newest, other stuff now, which is my friend Edmund also following that path. But yeah.
I see. So for your thesis, you've been working more independently. Okay, that's good.
Yeah.
Anyway, now with technology, it's a bit easier to work. You can still connect with your group in Australia. Like for me, I have a meeting 10 p.m. tonight because I'm doing a project with some people from America.
On Zoom. That's why.
It's definitely more possible than it was in the past, right? But okay.
Yeah.
Right. Good to hear that.
Mostly, I just downloading papers from archive and then read. Yeah.
That's good. Okay, I think that those are all my questions. Anyone else?
I have no question.
I have no question. Yes, Mia, I have a very small question. Even though I'm not in your field, because after I heard your talk, I feel blah, blah. But I'm more interested about the relation between your fields and the so-called quantum topology. And I know there will be, a very small brand of quantum mechanics. And that part is what I'm really interested in yet. So can you explain us something, or can you give us some example about the relation between your fields and the quantum mechanics or the quantum topology?
Yeah,
Thank you.
Okay, good. Yeah, actually this part is also interests me very well. So John's polynomial, when they come up with this John's polynomial, actually they are not really doing computation in the links, but they look at the stuff from statistical mechanics. So in statistical mechanics, they have these maybe they look more on the functional analysis part, but actually they extract out this algebra structure, which make this category theory interesting. So category theory is mostly aimed to connect algebra and topology. So in quantum mechanics, do you know much about physics? Sorry, like how much do you know about I can't hear. Sorry.
My major is physics.
Oh, your
my
major
major
okay,
is
good.
mechanics,
Yeah.
Not really physics, but major is mechanics.
Yeah, sure. Okay, thank you. I'm not really good in the physics, but I kind of connect myself connect the physics story myself. It's like in the so they are trying to relate this gravity to quantum mechanics. So because Einstein used the differential geometry to explain the gravity, but when things is really small, they found that actually probably is the government of the algebra structure of this element. For example, like the Feynman diagrams. Okay, Feynman diagrams like two atoms combine and then they shoot out another atoms. So this is somehow like this graphical calculus doing, because in the Chern-Simons theory, when they unify the three forces, they use the irreducible representation of Lie algebra. Okay, what algebra I'm looking here is actually the Heisenberg algebra. Can you see the diagram? Heisenberg algebra. And then Heisenberg algebra will be explaining the commuting boson. Yeah. So when I draw this graphical calculus, is somehow mathematical formulation of Feynman diagram. Something like that. Yeah. Yeah. This is what we categorization are doing. A lot of graphical calculus occurring, and then this is also because of physics is happening.
Thank you.
Yeah, thank you. Yeah, thank you.
Okay. Any more question regarding of the research or the mod teaching?
No question.